Yes, everyone. So we'll be resuming our discussion on the uh, viscosity here. Excuse me. Okay, so what do we notice with viscosity, right? So the first part, as we have seen here, that the viscous force between two layers of the liquid is given by neta A dou V by dou Z, right? So one layer of the liquid uh, experiences a force due to the bottom layer, a value equals to neta A dou V by dou Z, right? What is dou V by dou Z here? The Z value here is the distance, right? Z is the axis of the, let's say this is a river and this is the depth of the river. So Z is that vertical axis. And dou V by dou Z, dou V refers to the velocity gradient here. So as I said, that when the liquid is flowing through this channel, the velocity of uh, the velocity of the flow would have a gradient like this, right? Now, therefore, we can understand that there's a gradient to the velocity. That is, the velocity at the top is v here, and the velocity at the bottom is 0 here. So the gradient is given as dou v by dou z, which is basically, if you consider a small change in the ratio of the change in velocity with the change in depth, del v by del z. That's what is your gradient here. So yes, that's your viscous force calculation for the uh, for this stream of for the stream flow here. Shortly, we'll look at some more examples which will elaborate this more. And next one is here the Reynolds number. How is number talk? Reynolds number is calculated uh, as rho Vd by neta. What is this rho Vd by neta? It's basically the number. It gives you a final value, and when that value is greater than 3000, then you find that the flow is going to be turbulent. And what's a turbulent and a laminar flow, by the way? See, this part is something like, picture speaks much better than words. I've already shown you that. You see here a flow which is neither laminar, which is neither steady, that's characterized as a turbulent flow. Now, what's a steady flow? Steady flow is that where the velocity and the pressure, which are properties of the fluids that are flowing, is constant with time, right? That's a steady flow. And what's a laminar flow? Laminar flow is where the particles are just going in the same fashion at a given point. All the particles passing through a point are going in the same fashion. So essentially, a laminar flow will look like this, something which is very parallel and streamlined, and it looks something like a silky hair. Okay, and this looks like a frizzy hair. Okay, which is changing. The frizzes are also changing. It's not a constant frizzy hair. Okay, that's called a turbulent flow, right? You will be aware of this when you open the tap at a high speed. You'll notice that quite often the turbulence returns. Initially, at small speeds, the flow is very laminar, right? Okay, so yes, and there's a way to quantify the turbulence and the laminar nature of the flow as well. It's not just based on looks, right? Because physics, as we know, is all about quantification. So how can you quantify it? You quantify the flow based on the density of the fluid, velocity of the fluid, the diameter of the flow, and the viscosity, right? So the Reynolds number quantifies that. When the Reynolds number is greater than 3000, it's a turbulent flow, right? Which means it's quite going to be looking like what we have seen before, right? A little frizzy. And when the Reynolds number is less than 2000, it's going to be looking very laminar, and something in between would be a transient flow. So we'll be looking at some more examples of this Reynolds number as well. Coming to the third part of viscosity, the third property here, as we discussed, is the Stokes law. What is Stokes law? What is it going to tell us? You see, the raindrops which are falling from the sky. Let's just take that case. So raindrops, why are they falling down? Naturally, due to gravity, no other force pulling it down. But at the same time, if gravity is continuously acting, we know how much velocity gravity gives to the object which is falling, right? Consider a mass m which is only acted upon by gravity. So it has got an acceleration of 10 meter per second square, which means the del v per second is going to be equals to a into t. So per second is going to advance by 10 meter per second. Okay, so the raindrop which is falling from the sky onto the earth by the time it should reach the earth, it's going to be falling so fast that it's going to at least have a thousand, or it's like 1 kilometer per second kind of velocity if it were continuously being accelerated by gravity. But that's not the case, right? Because uh, there are other forces that are acting in the atmosphere as well, which prevents this from happening, right? Typically what happens is there is this force called drag, right? So this drag force is a property of the fluid depending on viscosity of the fluid. So due to that viscosity, what happens is it experiences a drag force which is proportional to the velocity of the fluid, velocity of the object that's falling through the fluid. Like for example, take a ball and throw it into the water, right? Or imagine for that matter a person who is diving into the water. So as the person dives into the water, what would happen? The person has got a velocity due to which it go very fast. But as he, the moment he lands into the water, there's a resistance, right? So that resistance partly is because of buoyancy. Definitely buoyant force is there. At the same time, you also have a drag force. Okay. So what is this drag force? This drag force is something which is in addition to the buoyant force, and this is proportional to the velocity of the fluid, that velocity of the object which is flowing in the, which is trying to move through the fluid, right? So therefore you would see that quite a lot of times you'll find that the comets that are entering the Earth's atmosphere, they would be burnt up. Why would they be burnt up? They would be burnt up due to this viscous forces. They experience such huge resistance that the viscous forces are doing a lot of work on that because they are entering with such a huge velocity, and the work that these viscous forces do is more often the drag and the other viscous forces, they do dissipative work, which means the energy is lost as heat, right? So when the energy is lost as heat, what happens typically? That time basically all of the energy which is lost is converted into heat, and it raises the temperature of the object to such a degree that typically these comets will be burned down by the moment they enter the atmosphere at such huge speeds. What to speak of small water drops, right? They would be burned down as well if not for this Stokes law, which kind of balances the velocity gain, right? So it wouldn't, the moment the velocity seems to rise, what happens? The drag force also rises, and at one point, the buoyant force, the drag force, and the force of gravity will balance out each other, and the raindrop will be falling through the liquid with a uniform velocity. So that's called the terminal velocity of the object that is moving through the fluid. Okay, so that terminal velocity v, if at all you know, then the way to find that is by referring to the Stokes law, which gives, especially for a spherical object which is moving through a speed v, the drag force on it is given by 6 pi neta rv, right? So this is the Stokes law. Now when we use the Stokes law, you know that basically the object which is moving down due to gravity amg, and at the same time it experiences an upward force of buoyancy. Also, this experiences the force due to Stokes law, right, which is the drag force Fd. So this Fb plus Fd equals the mg force, giving or telling us that the value of uh, net forces, the value of acceleration of this is zero, which means its velocity is constant. And so I can say that this raindrop is going to reach the earth with this speed only. It's not going to change its speed. Okay, so let's take some examples on this. So first consider the first example. It's on the same terminal velocity which we have been discussing. So find the terminal velocity of a raindrop of radius 0.01 millimeters. The coefficient of viscosity of air is given as 1.8 into 10 power minus 5 meters. 1.8 into 10 power minus 5 Newton second per meter square. That is the unit of viscosity. And its density is given as 1.2 kg per meter cube. Density of water is given 1000 kg per meter cube, and G is given, right? So as I said, the raindrop which is falling through the atmosphere, this has got a size R equals to 0.01 millimeter. Let's consider it for now to be a sphere, right? So Now the equations of motion on this raindrop is definitely the forces, all the forces that are acting on it, we'll be listing it down. So the first force that we have is the force of gravity, right? And the second force that we are going to see, right? The second force is the force of buoyancy, because it's in air and air is also a fluid, so air is going to exert the buoyancy force, and due to its velocity, right, it's already falling with a velocity v, so you will have a drag force ft. Now the resultant of all these forces put together is that this drop is going to have a constant velocity v, because the sigma f is going to be 0 on this drop, which means, you see guys, fb, which is the force of buoyancy, plus fd, which is the drag force, is going to be equal to mg, which is the force of gravity. So what do we have next? See, fb, the force of buoyancy, how much is that going to be? We've already discussed from the Archimedes principle, isn't it? This fb is just supposed to be equal to, yeah, the volume of the raindrop times the density of the density of the liquid, obviously, right? Because volume into density of the liquid is going to give us the weight of the liquid displaced, which is going to be the same volume of the raindrop. So into g, right, that's going to be your fp, plus the drag force. So I told you how much the drag force is going to be. This drag force is going to be proportional to the velocity. That means initially when the raindrop has got zero velocity, the drag force will be zero. But as the raindrop's velocity increases, the drag force will also increase. Okay. So the FD here is going to be equals to 6 pi neta r v, which is your drag force. So combination of these two is going to be equal to the force of gravity, right, which is equal to mg. So see guys, this is the equation of motion we have formed for the raindrop. Now it's about substituting the respective values only here, right? So one thing to note here, mass of the raindrop is not yet given. So what we'll do it like this. Mass of the raindrop is nothing but mass of the water, density of the water into volume of the water, right? So the volume would be equal to the same volume V here, right, of the drop multiplied by density of the liquid into G here. So yeah, it's not liquid essentially, but it is water specifically, because here water becomes the object and the liquid or the fluid here becomes the air. So uh, the equation for the dynamic equilibrium, right, is this. Let us substitute the rest of the values here to get the value of one unknown V. So V here is supposed to be equal to 4 by 3 pi into r cube, because that's the volume of a sphere. Here the value of r is already given. So this V multiplied by the density of the air, which is given as 1.2 kg per meter cube here, multiplied by G here, which is going to be 10, and so this will be your the point force Fb. Now this should be added with the drag force Ft, which is supposed to be equals to 6 pi into neta. What is neta? Neta is 1.8 into 10 power minus 5, and multiplied by the radius r, which is going to be 0.01 mm. So 0.01 into 10 power minus 3 meter. And what else? So into V. The V here is the unknown which we have to find. So equal to mg. So when it is equal to mg, the mg will also have 4 by 3 pi r cube, which is V, into the density of the water, which is 1000, into G, which is 10. So I want to find V, right? So V would be therefore equal to, if you take this other part, FB to the other side, you would have mg minus FB, which is going to be 4 by 3 pi r cube into 1000 into 10 is 10 power 4, minus, if you take 4 by 3 pi r cube common here, into rho of the fluid is nothing but rho of the air here. So that is 1.2 into 10. That's what we have here, right? 4 by 3 pi r cube into rho into G is this. Now that you are taking it to the other side, so you are subtracting it from mg. So mg is this value, subtracting it with this value, in which I have already taken common this thing 4 by 3 pi r cube, so it comes outside here. So you would just have to subtract 1.2 into 10 from this 10 power 4, right? Seems like a very small number compared to 10 power 4, right? So that is going to be equal to 6 pi neta RV on the LHS, right? Of which I'm going to send the rest of the terms 6 pi neta R onto the denominator. So these values would therefore be equal to 6 into pi into neta value we already seen here, 1.8 in 10 power minus 5, and so 6 pi neta R. So the R value is, let's keep it as R for now, 6 pi neta R. So you see R cube and R. So R cancels this and you get here R square. Pi cancels this, 4 by 3 by 6. If you solve all this, you will get the value of velocity V here, right? So this is called as the terminal velocity of the raindrop. So if you use a calculator, we'll get the value. Uh, let's proceed to another question. I'm going to leave this calculation. So it's basically another question from the fluid statics, but we are not going to take this right now. So okay, fine guys, all right. Uh, so now I haven't yet discussed any questions regarding the viscosity. Fine, but I wish to go to the next topic, which is yes. So here we'll be discussing this, right? So I've told you that the yeah, we have it here. So this is what we would be calling as a force due to the viscous force in the fluids, right? So it behaves just like the static friction that you see or the kinetic friction you see, right? You have a solid, you have another object, and what happens in the case of the kinetic friction, right? You have the mu here between these two surfaces, mu k. So mu k into n is basically the kinetic friction between this object and the ground, isn't it? If it has a velocity v. So something similar happens here as well, right? As the fluid flows, the flow of the top layer on the bottom creates a certain friction. So that friction leads to this value of drag force, which is equals to theta A dou V by dou Z. So the A area is basically the area of the fluid that you're considering, right? So let's say you take a layer A of the fluid area and you have another. So due to that, you want to find out the value of the force of drag. So that value would be equal to beta into this A into the gradient which you have for the velocity, right? Because one layer is static and the other layer is moving. So there's a small gradient here, dV by dz, which is there for the velocity. Excuse me. Right? So viscosity is a property of, just a quick small questionnaire to summarize whatever we've been discussing. Obviously, I know that you'll be considering its viscosity we have seen in the case of liquids, right? So two properties of it, the Stokes law and the Reynolds number, are discussing about these, and as well as the force due to the viscous flow, right? The viscous force due to the flow of the liquid we have seen, which is the liquids, and also we have seen the Reynolds number, not Reynolds number, but we have seen the Stokes law apply for gases, which depends on viscosity, right? So definitely viscosity is a property of fluids, right? What are fluids? Fluids are those which flow, okay? So typically we know that gases flow, liquids flow. So basically fluids implies it's a property of both liquids and gases, right? So this is the dimensions of viscosity. So this is one of the important things to remember, because not remember, but basically you should understand how that we can calculate the dimensions of viscosity also. See which formula should you use to calculate that. See, you can use the formulae where you know the dimensions of one of all the quantities except this. Like for example, the force due to viscous force is given as eta n dou v by dou z. So here you know the dimensions of velocity, you know the dimensions of length, you know dimensions. Here is area, here it's force, right? So here it is supposed to be kg meter per second square, and so that's basically dimensions of mlt power minus 2, right? So mlt power minus 2 is supposed to be equal to theta into the dimensions of area is L square, dimensions of dV is nothing but meter per second, right? So Lt power minus 1 divided by dz, which is dimensions of length here. So if you put it there, you'll find that length and length cancels here. L square, when it goes here, it becomes m L power minus 1. T power minus 1, when it goes here, becomes t plus 1. So t minus 2 plus 1 is t minus 1. That's your dimensions of theta, right? So you can have this as a prototype for calculating the dimensions of those quantities which you are not aware of, right? Sometimes questions would be asked to calculate the dimensions of epsilon, permittivity, or the permeability. You have to just do the same thing. Take the quantity whose dimensions you already know, and you just have this one particular quantity whose dimensions you are not aware of, and you just substitute the dimensions of the others to get the values of these, right? So we are not expecting you to remember these things, but you need to know the way to derive it. And typically there will be questions like this both in NEET as well as JEE. Okay, let us look at few values of coefficient of the viscosity in the case of the okay, in the case of a lot of different materials. And you see here the coefficient of viscosity for the castor oil, right? So typically the SI unit here is called poise, the unit of viscosity, which is the same thing which we saw, meter kg per meter second. So you see the value is quite high, 53, and the viscosity of air is very low. It's not 171, it's 0.171 because it's in micropoise. So into 10 power minus 3 you already have here. So which means the typically what we imagine, the oils have got a very high viscosity, right? And you notice that the viscosity is also varying with temperature. So this varying of temperature is also very something very easy to understand, and it's a property of the fluids. You see guys, typically why is this viscosity arising? So when you go back, you see there is one particular property of the fluid which is responsible for the viscosity. You can see here, right? uh, the directions are such that the relative motion between the layers is opposed. This property of the fluid to oppose relative motion between its layers is called viscosity, which is what we see. And the forces between the layers opposing relative motion between them are known as the force of viscosity. And they are basically arising here due to the value. So why are they arising here? So they are arising due to the it's the forces between the uh, molecules of these layers basically, right? Okay, so what happens to these molecules as they as the temperature increases? So we can very easily find out, yes, in the fluids, especially in the liquids, right? You notice in the liquids as the temperature increases, what happens? The separation between the molecules will increase, right? And therefore, the force which it exerts on the subsequent layers of the fluids, that will decrease, right? So typically, therefore, the viscosity is reducing as the temperature increases. You see here, from you go from 0 to 20 degrees to 40 degrees to 60 to 100 degrees, the viscosity is reducing gradually. And at the same time, you see for the gases, like for example air, you see that the value of viscosity is increasing with increasing temperature. Why is this difference between the liquids and the gases? It seems as though the property of viscosity was common to both of them. Yes, it is common to both of them, but the origin of viscous or the drag force is little different for the gases. For the gases, typically, you see the layers are free to move on one layer is free to move on the other layer. There's no typical interaction between the layers, right? Because the gases already the force of interaction between the molecules is very weak, so they don't exert the viscous force due to the internal friction, so to say. It is majorly because of the collisions of the air molecules on the object which is moving in. Okay, so it's like a lot of molecules are coming and hitting this, right? Due to the random motion of the gases. What happens when the object is trying to move? Let's imagine, for example, the same raindrop is trying to move down. So as the raindrop is trying to move, so there are a lot of air molecules which are unknowingly coming and bumping into this. Okay, so as they come and bump into this, naturally they will slow it down, right? Because the air molecules are going to transfer their momentum onto this into the other direction. So eventually what will happen is, as this is trying to go down, there will be a lot of air molecules which will bump into this and reduce its velocity, and it will create a drag to this. Okay, so that drag force, right? That drag force, so now due to that drag force, the liquid is experiencing viscosity. Okay, so what will happen as the temperature increases? Won't the motion of the molecules of the air become more, or will it become less? See, if it becomes less, then the viscous forces due to the air molecules will, or the drag forces due to the air molecules will reduce. But you notice that the velocity of the air molecules is going to further increase, right? So if the velocity is further increasing, when they go and collide with the air drop, what happens here? Water drop, what happens? You notice that the speed of this water drop is going to reduce further, and basically the drag forces are going to be increased further, isn't it? So you notice these values here of the drag forces, it's increasing as the temperature increases for gases, right? This is a slight difference between the liquids and gases. And what about the pressure? Will the pressure of the fluid, will it increase or decrease the viscosity, right? So for us, uh, we know that basically the velocity, the Vrms of the gas here is basically equals to root over gamma RT by m, right? So Vrms is basically, I think it's not gamma RT by, it's 3 by 2, it's uh, root over 3 by 2 nRT, or basically, uh, yeah, root over 3 by 2 nRT. I'm sorry, root over 3 RT by m. Yeah, if you consider just 1 mole or n moles, then it's root over 3 RT by m, right? This is your Vrms. So you see here it is independent of pressure. It's only dependent on the temperature. Okay. So as long as temperature remains constant, even if pressure is increasing or pressure is reducing, the viscosity won't change. So, but you look at the viscosity of the liquids. Naturally, as the pressure increases, the liquid molecules are going to come closer, right? The layers are going to come closer. So therefore, there the viscosity is going to increase with increase in the pressure. All right. So that's the dependency on temperature as well as on the pressure, guys, of viscosity. Fine. Um, let's take some questions here, right? So we saw already what is this Stokes law, which is 6 pi neta RV, right? Which is basically when a spherical body moves through a liquid of viscosity neta, the viscous force acting on it is given as 6 pi neta RV, right? So let's take a small question here, guys. So a spherical ball is dropped in a long column of a viscous liquid, and the speed of the ball as a function of time. How is it represented as? Let's try to solve this question, guys. Okay. So to solve this, um, we need to know basically what are the forces acting on the spherical ball, right? So obviously the forces are the same, right? The force mg and the force of buoyancy and the force of drag ft. So we know that the drag force here is supposed to be equals to 6 pi neta rv, or it's basically a constant k into velocity v, and the force of buoyancy is a constant, and mg is also a constant. So if I say the mass m into dv by dt, which is the acceleration of the object downward, is going to be given as mg minus, you will have fb here, minus you have fd, right, which is basically sigma f. If you take the downward direction as positive y direction, so mg is positive and both these are negative. So mg minus fb minus fd is supposed to be equals to ma. M into a is given as dv by dt. So I know that so you can see here the acceleration of the object, right? So it's a v versus t graph. So dv by dt, which is the slope of this graph, is supposed to be the acceleration. So first, let's understand what's going to happen to the acceleration. So acceleration is going to be g minus fb by m, which is also a constant, minus fd by m here. So what is this fd by m? Fd by m is just going to be the force of uh, the drag divided by m. So it is 6 pi neta rv by m. So it's dependent on uh, velocity v, right? So initially the velocity is 0, so the acceleration is high, which means 10 meter per second, let's say, for example. And later on, what happens due to this acceleration, the velocity is going to, let's say, after 1 second, the velocity is going to be definitely more, right? So as the velocity increases after 1 second, what happens, guys? Let's say here the velocity is 0, acceleration is 10. Uh, let's assume close to 10. Definitely it will be a little lesser than 10. Now, in the second case, after 1 second, like t equals to 1 second later, what's happening to the velocity? So the velocity will be increased. It won't be 0. It will be something like 1, let's say. So that time, the acceleration is going to reduce, right? Instead of 10, it's going to become something like 9 or 8, whatever, right? Because here you're going to have the v, which is increasing. So you're subtracting from g more. So your acceleration is going to drop to, let's say, 8. So which means uh, you see the value of a should be reducing. First of all, that's the first criteria. So out of these graphs here, a b c d, you can notice only two graphs where the velocity is reducing, which is c and d, right? So that is the I'm sorry, not so first of all, this is not a graph of A versus T, this is a graph of V versus T. So what should happen here is the slope should reduce, right? And what happens to velocity V? Velocity should increase, right? So which graphs here has got a velocity which is increasing? You can notice D, it's not the case, C, it's not the case. A as well as B are both cases where the velocity is increasing. So the correct answer is supposed to be either A or B. And the other thing that you notice is the slope of this, which is acceleration value, right? So acceleration value is reducing. So it is 10, 8, 7, 6, like that it reduces with time. And so the slope of V versus T should reduce. It cannot be a constant value. In the option A, it's a constant. So that's also not a right answer. So the correct answer in this case is supposed to be B, right? Where the velocity is increasing, but the rate at which it's increasing, that is decreasing, right? Because the acceleration is going to reduce slowly, right? And at one point of time, it's going to reach 0. So the slope is going to approach a 0 value. It's going to flatten up here as you go further in time. So the correct option is supposed to be B here, guys, right? And from this graph, you can notice that you see the slope is reducing. Initially, the slope is this much. Later on, the slope has reduced because tan theta has reduced for these graphs, right? Because the theta is reducing. The theta is lesser than this theta here. This quite lot, right? Theta 1 is more than theta 2. So the slope has reduced. All right. So that's about viscosity. Let's take another question. Okay, let's take another question on viscosity here. As you can see, a solid ball of volume V experiences a viscous force F when falling with a speed V in a liquid. If another ball of volume 8V with the same velocity V is allowed to fall in the same liquid, it experiences a force. So basically, you're just comparing the viscous forces. How to do this question? Just note down the formula for the viscous force, right? So the viscous force or the drag force is given as 6 pi neta RV. So due to the first ball, it's going to be 6 pi neta RV. Let's take the volume V. Then the volume V corresponds to a 4 by 3 pi R cube, right? Let's say it is R1 cube corresponding to V1. Now the second ball has got 8 V1 and right, so its volume is supposed to be 4 by 3 pi R2 cube, right? So corresponding to that, the drag force FD2 is supposed to be 6 pi beta R2 into V. So compare these two guys, compare these two forces. You can find that it primarily depends on R1 and R2 basically because the other values are same. 6 pi neta V are same. So R1 and R2 are to be compared here. So you can notice if V1 and V2, so V1 by V2, which is V1 by 8 V1, supposed to be equals to R1 cube by R2 cube. So you get that as 1 by 8, which means R1 cube by R2 cube is supposed to be 1 by 8, or 1 by 8 whole power 1 by 3 is supposed to be equal to R1 by R2. So what is this value? 1 by 8 power 1 by 3, that's 1 by 2, right? So R1 by R2 is 1 by 2, which means R2 is equal to twice of R1. So therefore the force due to the drag on the second ball supposed to be 6 pi neta into R2 is supposed to be 2 R1 into V. So you can notice this is going to be twice that of the force on 1, right? So so if it falls with the same V, then it experiences a force equals to 2F, right? So this is another model of question, and so let's take another question, um, which is from the mains 2020. So in an experiment to verify Stokes law, a small spherical ball of radius r and density rho falls under gravity through a distance h in air. So it initially falls under gravity through a distance h, right? Before entering a tank of water, before it enters a tank of water. If the terminal velocity of the ball inside the water is same as its velocity just before entering the water surface. So whatever is the velocity v here, if it's the same velocity as the terminal velocity, right, then the value of h is proportional to, right? So first what we have to do, see here, v equals to vt is a condition that's given to us here. So which means every liquid, see what is the terminal velocity inside the liquid? So that velocity is going to be when the force of buoyancy and the force of the drag, right? When these both forces equals the gravity, that's what is going to be the terminal velocity. So it's independent of with what velocity you come in inside, right? It's totally irrelevant to that. So there's going to be only one velocity for a given fluid. Okay, that's going to be a unique value, right? For a given fluid and for a given object, because it depends on FP and FD. So for a given object inside a given fluid, you have only one velocity, which is the terminal velocity. So how will we calculate that? Let's say you just calculated it already, and that is Vt. So that Vt should be equal to the velocity V of this ball when it is dropped from a height edge, right? So if you know this, pretty much the problem is over. So how to know this Vt? So just see this equation. Fb plus Fd should be equal to your value of mg. So we've already solved this partially. Fb is supposed to be volume of the object into density of the liquid into the G, and Fd is supposed to be 6 pi neta Rv, supposed to be m into G. M here is nothing but volume of the object, volume of the object into density of the object into G. So the value V is supposed to be equals to V G. Take this to the other side. Rho of the object minus rho of the liquid divided by 6 pi neta 6 pi neta, right, into r. That's your v, which is your terminal velocity of this liquid here, right? Terminal velocity of this object. So equate this value to vt, and this vt is supposed to be equal to your velocity of this object as it has flown, as it has fallen down to a height edge. So we know that an object which is dropped and falls a height edge, its speed v is supposed to be equals to root over 2h by g, right? So equate that. Root over 2h by g is supposed to be equals to this value here, vg rho minus rho L by 6 pi neta r. So it's basically it's basically everything here is a constant. For v is the volume of the object, g is the gravity, rho is the density of the object liquid, and neta is the viscosity of the fluid. It's all constant. So k by r we could say, because we are finding the dependency on r, right? So 2 root over 2h by g is supposed to be k by r. So your h is supposed to be k by r square, right? So the value of h is proportional to, and what do we have here? By the way, it's not k, it's not k, it's v by r. V is the volume of the object, right, which is 4 by 3 pi r cube in itself. So r and r cube cancels, you'll have r square here. So k here inherently is dependent on r cube basically. So k r cube I could state it because I want to find r. I cannot ignore v is constant. V is the volume of the object, the ball, which is dependent on r. So it is dependent as 4 by 3 pi r cube. So 4 by 3 pi r cube by r would be basically k r square. That's the dependency, final dependency on uh, on the terminal velocity. Yeah. So now I have h should be equals to k r power 4, right? So the h is supposed to be proportional to r power 4 is our answer. All right. So what we'll do is we'll end it here.